In 2024, Joël Lapointe was doing something completely ordinary, looking for a remote place to camp in northern Quebec. While tracing forest routes on Google Maps, he noticed a shape that did not seem ordinary at all, a huge faded circle wrapped around Lake Marsal. The feature was subtle. From ground level, much of the landscape looked flat and heavily eroded. But from above, Lapointe could make out a broad depression and a smaller ring inside it. He was an amateur astronomer, and the geometry reminded him of an impact crater. There was one problem. The structure was not listed in the crater databases he checked, so Lapointe began emailing experts. Most possible craters reported from satellite images turn out to be volcanic features, erosion, glacial landforms, or simple coincidences. A circle on a map is a clue, not proof. Eventually, the observation reached geophysicist Pierre Rochette and colleagues at Zircons in France. Their first task was to test whether the landscape made geological sense as an impact site. In a 2024 Meteoritical Society abstract, the team described a circular depression more than 15 kilometers across, with a faint inner ring roughly 8 kilometers wide. Existing geological samples also contained an unusual breccia, a rock made from broken fragments fused into a new material. The textures, magnetite, sulfides, and zircons in those samples looked suggestive of impact melt, but the researchers were careful. The abstract called Lake Marsal a serious candidate, not a confirmed crater. To settle the question, they needed evidence that could only be created by an extreme shock, or they needed to go there. In October 2025, an international team flew into the remote Côte d'Or region by floatplane. The terrain was rugged, access was uncertain, and the feature itself was difficult to recognize from the ground. Millions of years of erosion had softened the shape that looked so striking from above. The team's most important target was a geological structure called a shatter cone. These are distinctive, radiating fracture patterns produced when an intense shock wave passes through rock. On Earth, they are strongly associated with hypervelocity impacts and nuclear test sites. According to the researchers, they found decimeter-scale shatter cones in the ancient basement rock near the center of the structure. That was the diagnostic evidence the earlier investigation had been missing. They also reinterpreted the so-called Marsal breccia. What had once been described as a volcanic pipe deposit now appeared to be a thick sheet of clast-pore impact melt rock. The remains of local rock heated and transformed during the collision. The 2026 abstract reports that this unit may be as much as 50 meters thick and contains fragments of basement rock up to 50 centimeters across. Together, the shatter cones and impact melt change the story. The new abstract identifies Uhackatik as a hypervelocity impact structure roughly 25 kilometers, or 15.5 miles, wide. But identifying an impact is only half the mystery. The next question is when it happened. The team collected oriented cores from the impact melt rock for paleomagnetic analysis. When molten rock cools, magnetic minerals can preserve the direction of Earth's magnetic field at that time. Researchers can compare that recorded direction and polarity with known intervals in the planet's magnetic history. Their results suggest an age near 390 million years, during a period when Earth's magnetic field had reversed polarity. But 390 million is not an exact timestamp. The conference abstract gives a wider interval of roughly 370 to 400 million years. Preliminary lead isotope measurements from zircons in the melt rock provide separate, but still broad, support in the range of about 350 to 400 million years. More work will be needed to tighten the date. That distinction matters. As of July 23, 2026, the detailed result appears in a Meteoritical Society conference abstract, not yet in a peer-reviewed journal paper. The reported impact evidence is strong, but the age remains an estimate with a substantial range. The name Uhackatik was selected after consultation with a local Innu council. The discovery also preserves an unusual chain of credit. A curious observer noticed a pattern, scientists treated it as a testable hypothesis, and field evidence transformed that hypothesis into an identified impact structure. Google Maps did not prove that a meteorite struck Quebec. It revealed a shape that raised the right question. The proof came later, from broken rock, melted stone, magnetic memory, and an expedition into difficult terrain. And that may be the strangest part of the story. A structure roughly 25 kilometers wide survived for hundreds of millions of years, worn down until it nearly disappeared from the ground, yet still visible to someone curious enough to stop, zoom in, and ask what made the circle.